First of all, thank you all for attending the seminar. I think we have quite a few people here, so it's great to see that there is so much interest in this topic. Obviously, I think it's very, very interesting since I'm doing this work. And I hope by the end of the presentation, you will feel so too. So today I'll discuss a bit about the methods that we use to predict deterioration of critically ill patients. And I will talk a bit about challenges that we usually face when we try to apply AI and machine learning in medicine. Before I start with the presentation, I would like to acknowledge the co-authors of this work. So my colleague Bruno from Fondazione Bruno Kessler, and then the clinicians, Wesley from National University of Hospital in Singapore, Louis from University of Southampton School of Medicine, David from University of Virginia School of Medicine, and also Leo from MIT and Beth Israel Medical Center. I should mention that this is the work that took over 6 months, in fact, to complete. So obviously I will be skipping a lot of details, but I will only focus on the the main parts. Okay, so as an overview, I will talk a bit about why we did this work, what was our motivation. Then I will talk about problem definition, and here I will stop a bit more and focusing on challenges in machine learning applied to medicine, and why it's different, for example, when you apply machine learning in other domains, for example, computer vision, natural language processing, or even human activity recognition that some of the people here are very familiar with. Then I will talk about how we addressed the problem, what methodology we used, the results we obtained, and finally I will talk a bit about what were the main findings and what is the future plan. Okay, so in terms of motivation, intensive care units generate large quantities of data, and this data is generated in continuous manner. Of course, humans are limited in actually processing large quantities of data, and this limitation obviously extends to ICU clinicians as well. Therefore, there is always a risk of not recognizing early warning signs of deterioration due to information overload, and as a result, then it might lead to delays in actually treating deterioration patients and affecting the final outcomes. So we know why we are doing this work, but how actually we define the problem. Before I go into the problem definition, I want to talk a bit about why machine learning for medicine is different from the other domains that I spoke about. So we know that machine learning has been very successful on well-defined problems where solutions are easily verifiable. For example, majority of the people agree what a cat is, and they can label the picture either that contains a cat or not. And of course, then once the models are, trained and they are developed, it's relatively easy to verify, how well the model is doing. Or even in terms of human activity recognition, for example, majority of people agree, what is the sequence to carry out a specific activity. But in medicine, the problems are not well posed. So the solutions to those problems are difficult to verify. For example, today, I'm talking about deterioration, but the question is, how do we label something like this in terms of machine learning? Then, of course, once we have a problem defined and a solution, then there are other challenges in terms of data. So typically in medicine, data is limited, meaning that, you have to work with what you're given. So you cannot go into the wild and collect more data. Data could be missing. And this is an issue because the fact that the data is missing might be informative as well. So, for example, the fact that an intervention has not been recorded, it's difficult to say whether the clinician judged it as unnecessary because of the patient state, or it has been reported due to an error. Then data might be biased. Of course, this is true for many data sets in machine learning and AI in general. But for example, especially in medicine, ICT codes sometimes are used for carrying out research, but these codes, in fact, are optimized for billing. And then, data might be noisy. So if we want to do things like outlier detection, we cannot simply apply a formula, but it needs to be based on clinically relevant intervals for each variable. And also sometimes these intervals are not very well defined. And of course, the models that we create, they must be explainable. And this is still a very big challenge for longitudinal data, because we need to understand not only what variable is relevant, but also at what time. So this creates enormous challenges. But of course, whenever there are challenges, there are also huge opportunities to really transform medicine. So coming back to our problem, in terms of machine learning, I asked the question how to actually label deterioration. Now, as you can imagine, if you ask clinicians what patient deterioration means, you will probably get very different answers. So the clinicians that we worked with were especially interested in lactate, and I will explain a bit what lactate is. So lactate is a measure of lactic acid in the blood. What that means is that lactate levels actually increase if oxygen isn't readily available. So for example, even if you are doing strenuous exercise, that causes an increase in lactate levels. But the difference is that for healthy individuals, lactate is cleared by the liver. However, in patients, the lactate remains in the blood. And this is the two studies that we have done very recently, where we found that high levels of lactate, so greater than or equal to 10 millimole per liter, were associated with 79% hospital mortality. So as you can see, lactate is definitely a very good indicator of patient state and can predict deterioration. Of course, the story is not finished, because if we have these lactate levels, how much of an increase actually should be labeled as deterioration? So lactate levels range from around 0 or close to 0 up to 30 millimole per liters. So we looked, of course, at the clinical guidelines, and then we found out that, for example, some guidelines suggest that if a 10% increase in lactate levels elevates the risk of mortality. Some other guidelines suggested that it should be a group-based approach. So we group the patients, if the lactate is less than 2, we group them into a normal group. If it's mild, from 2 to 4, and severe greater than 4. But then, you see papers like this. So these are the 3 papers that have been published in 2016. And obviously, first and second are very much contradicting each other. And the third one, we are not really sure. So I think what this highlights is that it is very important, actually not very important, but it's fundamental to work very closely with the clinicians in defining the problem. So for our needs, this is how we define the problem. So what we have here is we went with a group-based approach. So we have patients in the normal, mild, and severe. And then for each of these groups, we define 2 outcomes, a negative outcome and positive outcome. So, for example, if patients are in the normal group, if the lactate increases to mild or severe, it's considered a negative outcome. Then same for the mild. For example, if the lactate increases to severe group or even remains with the mild group, then it's a negative outcome. And the same with severe as well. And then, of course, the opposite of this, we have the positive outcomes. So if the patients remain within the normal group, this is considered a positive outcome. If it decreases, if from mild decreases to normal, it's positive, and so on. So since we also saw the guidelines that were suggesting 10% increase in lactate levels, then we also provided an alternative definition outcomes. So if 10% is an increase, we label that as deterioration. Okay, just to give you a kind of a visualization of this problem. So the red arrows indicate lactate measurements. So what we have here, this is the legend. We have observation window, prediction window, which in our case was 2 hours, and then lactate measurement. So the patient gets admitted to the EICU, to EICU. Then at time T0, a lactate is measured. And then there are some variables over time that are measured here. So our objective is to take the variables that have been measured in this time and predict the next lactate 2 hours before. And then we also repeat this process for the subsequent lactate measurement. So then this one becomes our reference point, reference time. The variables are, of course, are measured, and then we make the prediction. Something that we also tried, and you can see on this grayed out arrow, we also tried to extend actually the observation window. So what we wanted to do here is to incorporate all the past information in order to predict the subsequent lactate measurements. However, in our case, the results did not improve. And this could be because of the nature of this problem. So perhaps for lactate prediction, past information maybe is not very relevant. So we have the problem defined now. How did we address it? So in terms of methodology, we used 2 large clinical databases. These are well-known databases. One is Mimic, that has 61,500 ICU admissions, and EICU CRD, which has over 200,000 admissions. Now, I should mention here that Mimic is a single center database. And what that means is that all the data is coming from a single ICU. And typically, in terms of data analysis, Mimic data is typically more homogeneous. Whereas for EICU, the data is coming from 335 different ICUs and 208 hospitals. Then, of course, we had to define our patient selection criteria. So we focused only on the adult patients that had the length of stay at least for 24 hours. And then, since we are actually predicting the subsequent lactate, we had to ensure that in our data set, the patients that we selected had at least 2 lactate measurements in the first 48 hours. So from these data here, we came to an overall patient cohort of close to 30,000 patients, and it was divided with Mimic of 12,500 and the ICU 17,500, more or less. And this is our selection diagram. So I think what you will see basically here is that even though we are starting with 2 quite large databases, what we end up here is, a number of a cohort significantly reduced. And I think this is, another aspect of challenges in health, in medicine, especially in healthcare in general, where you really need a lot of data, because by the time you apply your selection criteria, you end up with a much smaller amount of patients and data in general. Okay, so in order to create the model, we selected 54 variables. And these were the variables that were common to both data sets, to both MIMIC and EICU. And these variables were categorized into 4 categories: so lab, clinical observation, treatment, and demographic. I should also say here that, also this work harmonizing the 2 databases took a substantial amount of time, because different variables are coded differently, obviously, because they come from from many different hospitals. So, for example, we had variables with different names. Also, some variables were recorded on different tables, and the same conceptual variable, but with different units. So we had to look through the distribution of each of the variables to make sure that they are similar. Of course, as I mentioned, with clinical data, the issue of missingness is significant. So for this work, we actually evaluated 12 imputation strategies, and this is described on this paper here. The strategies ranged from simple mean values up to using autoencoders. What we found is that the best performing method was indicator variable. Now, what this means is that for every clinical variable or demographic that you have, you actually add another dummy variable that indicates whether the value is missing or not. Of course, this has a significant negative impact on interpretability, because first, the number of variables doubles, and the second is that the dummy variables are not relevant for interpretability. So what we've done is we looked at the next best performance, which was fill forward imputation. So meaning that we carry data from the past into the current state. And for some variables, this was not possible. So we sat down with the clinicians, and they suggested us to use a specific strategy depending on what they thought it was the most appropriate for each of the variables. So there was not, let's say, one single strategy that we used for imputation of missing values. In terms of model development, so we compared three algorithms. So we used, as usual, logistic regression as a baseline, then random forest and LSTM. Hyperparameters using, obviously, random search. And then we had 2 types of validation. So internal and external. In terms of internal validation, we used stratified cross-validation, and this was done separately on MIMIC and EICU. And then for external validation, what we have done is we've derived a model on the EICU cohort, and then we used MIMIC as a test cohort. So obviously, you can see here that it made sense to actually derive the model on EICU because it was bigger, and then to test it with a smaller data set. And then in terms of interpretability, we used SHAP, which is quite a popular method to actually provide variable ranking and how they impact model predictions. Okay, so in terms of results, as you can imagine, there are quite a few results, so I won't stop for each of these, but I will only highlight 2 or 3. So in terms of internal validation on the MIMIC cohort, what you can see here is that we are doing very well for the mild and for severe group. So we are able to predict the next lactate with pretty high performance for these 2 groups. For the normal group, even though AUC is acceptable, precision recall is low. And one of the reasons was that the normal group was highly imbalanced. And what that really means is that the patients that actually had normal lactate levels continued to have normal lactate levels. So there were very few patients that actually deteriorated. So, which of course, it's a very good thing for the patients, but of course it creates a challenge for the prediction algorithms. Then we did a similar validation, internal validation on EICU, and the results were quite similar. Then I want to stop a bit more here because we also did an external validation. So typically, when you do an external validation, so you train a model in one patient population and then test it in another, you really expect the results to decrease, sometimes by a significant margin, because it could happen that the case that the distributions are very different, or simply the patient populations are very different. So what we found here is that this was not the case in our work. So both LSTM and random forest showed a very, very similar performance. Now, what's interesting to note is that the gap between logistic regression and the two other algorithms, so LSTM and RF, increased. So what this could indicate is that LSTM and RF were able to generalize better than logistic regression. So as I said, also, we provided this alternative definition of deterioration in terms of sensitivity analysis with 10% increase in lactate. And predicting deterioration here was much more difficult, so the results were lower with respect to the group-based approach. Okay, and lastly, we also did sensitivity analysis on restricting actually time window between measurements. So what we wanted to do is to investigate whether the restricting the observation window to 8 hours would improve the result. We chose 8 hours because lactate measurement guidelines suggest measuring lactate every 6 hours. Of course, this doesn't happen always in clinical practice, and neither was true for our data set. And then, so the guidelines say every 6 hours, plus we added 2 hours to accommodate for the fact that it may take some time for the values to be recorded. So what we found here is that the results did not change significantly for mild and severe. So we had a pretty similar performance. However, the results for the normal group increased slightly. So what this probably would mean is that if we restrict the time window to 8 hours, the normal group becomes more balanced. So because obviously the patients that are critical, they tend to have their lactate measured more often. So by dropping let's say the patients that are stable, the data set becomes a bit more balanced and the performance increases. We also looked at interpretability. So this is output of the SHAP method for each normal, mild, and severe group. So what you can see here is that lactate, so the previous lactate measurement is quite predictive of the next lactate. Now, this was to an extent expected, but some of these other variables that we have here, some of the clinical variables were less expected, and I think this definitely requires a further clinical investigation. And finally, we also looked at the calibration. So what we can see here is we have the 3 groups and we have the 3 evaluation methods. So internal evaluation mimic, internal EICU, and then external evaluation. What it shows here is that for the model that was predicting the normal group was overconfident with the predictions, meaning that the output probability was higher than the actual outcome. And then, of course, another thing to note here, although it may be obvious, is that, for example, for LSTM, calibration was much better in the internal validation than external validation, which, of course, is to be expected, perhaps due to the differences between the distributions. Okay, so in terms of discussion, so now I'm coming really to kind of the last part of this presentation. What were the main findings? So our results really prove that it's possible to predict lactate and also provide early warning signs of patient deterioration using machine learning methods. In our case, LSTM was best performing. But what was interesting is that there wasn't a very large margin with random forest and logistic regression. This could be due to the nature of the problem, where I said past information perhaps is not very relevant, and as such, the LSTM sequences that we had were quite short. So what this means is that both RF and logistic regression were actually able to capture the relevant information. In terms of interpretability, we need to further investigate how the impact of other clinical variables, how the other variables actually impacted the prediction performance. And then last thing to note here is that in this work, we could not include the treatment. So if there were drugs administered or fluids to these patients, because this information was not available. So if we manage for let's say a future data set to also include these aspects, I think the results are likely to improve, because it's the actual administration of treatment that significantly affects lactate levels. And okay, so then this is my last slide. So I want to stop a bit more here. So this was the first study to actually investigate prediction of serum lactate. And I think one of the things that this study has showed is how complex is lactate metabolism, because it depends on the disease that the patient has, response to therapy, treatment that has been administered, and perhaps it has a genetic basis as well. And all this information is currently not captured by the models. So we are only seeing, a kind of a small window into the patient state. And even though it's a very small window, we still managed, I think, to establish models that were performing quite well. Of course, now the question is, how do we actually verify the clinical utility? So what I said at the beginning, how to verify ML solutions in medicine. So of course, one way is a prospective study. But even if we do a prospective study, there are several questions that are open right now. So one of these is, what should we really be optimizing for? So if we want to optimize for prediction of negative outcomes, what that would mean is that we would be able to detect early signs of deterioration. And hopefully that would have an effect on reducing organ failure, reducing length of stay, and the final outcome, so mortality. Now, on the other hand, if we want to optimize for prediction of positive outcomes, then that will have the effect of reducing unnecessary testing, meaning that it would reduce the risk of infection, it would reduce the amount of blood that's wasted to actually do the test, and the hospital costs. So these two, it's impossible to have both. So I think these are kind of the questions that probably do not have a universal answer. And I think they probably will depend on case-by-case basis. So with this, I will conclude. And I will say that for studies like these, we are very much open to collaboration, both from machine learning point of view and clinical point of view. And I am happy to take any questions.
Thank you very much, Venet, for the very interesting presentation. Okay, so who wants to go first? Bjarne?
Mm-hmm. All right, so thanks first for the very interesting talk. We actually did a quite similar thing with predicting complications after pancreas surgery on ICU. And so I was interested in a few things actually. So first of all, of course, some of the features that you used are time series features like the heart rate and so on. So I was wondering how you were dealing with this for the more static models like logistic regression and the decision tree or random forest actually.
Yeah. So the usual ways is really either to put them into a single vector or to extract some of the features. So for this work, we actually put the time series feature into a single vector, and then they were considered as an input to both logistic regression and random forest. So this is what we've done. But I should mention that in here, due to the nature of this problem, the actual sequences were quite short. Mm-hmm. So because our, let's say our binning interval was 2 hours, meaning that at most we had 4 or 5 sequences, so 4 or 5 measurements before. Mm-hmm. So this did not represent a very big problem. Of course, if you're going further in the past, then perhaps some other methods might be more appropriate.
Okay, and also similarly, I think both databases that you used have quite different frequencies. So I think EICU has a higher frequency of measuring data points. So how did you deal with that also for the LSTM input?
So we binned the data. So we chose a 2-hour window. And mm-hmm. then we took the data over those 2 hours.
Yeah, but then, I mean, between the two databases, you might have 10 blood pressure measurements or heart rate measurements in the one, and then only 4 in the other, or was it exactly the same, actually?
If I remember correctly, so this is something that probably my colleague Behruz would know better. However, if I remember correctly, we chose the last one, so the closest to the interval, because those were the most representative of the patient state.
All right.
And then we discarded the others.
Mm-hmm. And then one more thing that was also quite an issue for us was the input of static data into an LSTM. So patient information like the age and so on obviously doesn't change over time.
Yeah.
You don't have more than one measurement. So how did you put that into the LSTM?
So this is, I don't remember this. This is something that my colleague knows. But I remember that we had a discussion on this point. So unfortunately, I cannot answer this question right now, but if you send me an email, I'm happy to provide the contact information and the answer.
Great. Thanks a lot.
Yeah.
Thank you, Bjarne, for the question and the discussion. Okay, do we have another question for Venet? You can either do it by raising your hand or, I mean, there is an option below there, or just unmute yourself and ask the question, or you can even write the question and I'll read it out loud.
I'll just go ahead and ask.
Yeah.
So we saw that the previous lactate value was the most important predictor. Do you know perhaps how well you can predict using just this variable? because this could be a pretty reasonable baseline.
Yeah. No, I think that's definitely a very good question. So I think this kind of analysis we haven't done yet, and these are analyses that are definitely very important, very useful. So, for example, obviously, taking the previous lactate and looking how well it predicts the next one is the first step. But then we should also try to reduce the number of variables because for us, we had 54 variables. And, in terms of simply computational power and to reduce the amount of computation that needs to be done, I think as a next step, what we need to do is we need to take perhaps, the top 5 from each group and then see, for example, how predictive are those with respect to the overall model. So this is definitely a direction that we'll go towards in the future.
Okay, thanks.
Thanks.
Thank you, Mitya. Okay, do we have another question? Okay, I'll maybe comment a little bit. So as you said, tackling these medical data sets and this e-health, if I may, it's not straightforward machine learning task. So if you define it well as a, supervised learning program, then probably you will solve it in a way, let's say. But the point is here how to define it properly. And so I know also with the problem that we are solving in the project with Bojana and another one that we are doing with Emilia. So it's not an easy task.
Yeah.
So
yeah.
How much time do you spend on defining the project in this kind of data set? Yeah.
So this exactly. You're right, and this took quite some time. Because I think, when you have people with computer science background and the clinicians, of course, the language is not really the same. And simply going, so if a clinician says, okay, I'm interested in deterioration, from machine learning point of view, it's very difficult, I think, to know how to actually transform the problem into a machine learning problem, let's say a supervised learning problem. So this took quite some time. So this took several months, in fact, to come to a definition of the problem such that we can apply the algorithms themselves. And this is why, as you probably saw on the team, so it was myself and Behruz from machine learning point of view, and then the rest of the authors were all clinicians. And each of them, had their own ideas and provided their own input to arrive to this problem definition. And then, of course, in addition to this, what we have done here is really simply the first step, because we've proven that, okay, if you apply, let's say, machine learning algorithms, lactate can be predicted. But of course, how do you actually verify that this kind of work actually changes or impacts the patient outcomes? And that's another significant and huge challenge that we'll need to explore, obviously, in the future.
Okay. Did you take a look into this bias problem in medical data sets in this analysis or not?
Not on this one, no. So this is something that we'll do with you first,
yeah.
and then we'll see. But we already know, for example, we did not use ICD codes because, as I said, they are really optimized for billing.
Yeah.
So to actually define the patient diagnosis, we used Apache. which is a clinical scale to say. Well, it's a clinical standard that defines the patient diagnosis. So this is what we used in this work.
Thank you. Do we have some last question? It doesn't have to be last. I think we can have a few more if there are any. Okay. Then let's wrap up. So thank you, Venet, for the very interesting research that you have done and you have shared with us. So that will be all for today. If you're interested in this kind of topics, yeah, you can follow us also on Twitter, LinkedIn, but also you will get notifications whenever we have some news or a seminar to share with you. So thank you all for joining this seminar and have a good afternoon.